All right, so I pretty much finished chapter 14 on last Wednesday. But there's one more thing that I wanted to do, but I'm just going to go ahead and establish that the quiz on chapter 14 is next Monday. And you'll be doing a lab tomorrow, so it should be ready for you to print out. See how well this is going to work.
Worked pretty well, huh?
Yeah, except we're not using the pendulum this time. Probably should get rid of, at least get this stuff out of the way.
I didn't know we did a chapter 14,
The
or for most of it. Maybe
simple harmonic motion was chapter 14.
oh. So it's the last bit.
The last bit. Sure. It seems like we did chapter 13 the first day. Or was that the first week? We've done a couple days on chapter 14.
Oh.
And somewhere there's a slinky out here that is so incredibly damaged. Here it is. It's around here somewhere. Now, it still holds the properties that we're looking for here. It's just that it's gotten mangled, and so it no longer has the same spring constant that it originally had. So what we're going to do, and similar to what you'll be doing in the lab tomorrow, is we're going to get this suspended right here, and then we're going to let that oscillate up and down. And I'm using this one because how much more damage can I do? Now, when doing this lab, I need to somehow keep part of it secure, because I've seen a number of people, they'll get it set up, they'll do most of the lab where they have it a certain way, and then it falls off, and where was it before? Because that has a different spring constant than that does. And so if you don't put it back in the exact same place, it will not work as well. And so now I've done something I should not have done. But at least it's being videoed so that my incompetence will be telegraphed to the world. Eventually I will cut those rubber bands. And so what I want us to do is predict what the period is going to be of this linking. Now, when we do our predictions for simple harmonic motion, we have that the period is equal to 2 pi times the square root of m over k. And if you're going back and forth between is it m over k or k over m, well, on the quiz or test, you'll have the equation on the first page. But also, the more mass there is means the more inertia, which means it's going to be more sluggish. So as I increase the mass, it takes longer. Imagine pushing a small child versus pushing an elephant. And just imagine it, don't do either, actually. And then spring constant deals with the stiffness. The spring constant deals with how quickly does it want to get it returned to normal. And so the greater the spring constant, well, that's going to snap back much faster because more force is being exerted per distance. However, what mass do we deal with here?
Mass of the spring itself.
The entire spring?
This one has the part of the thing.
Then how do we figure that?
Way before him done.
You weigh it.
You could weigh the total weight of the slinky and then figure out how much of the slinky is below by measuring the wiggle or something, and then figuring out the proportion.
That would be fine, I would agree with that for finding the mass of this. I actually have not tried that. I did it a different way. And so I'm curious now to find out if does that work. So let's do it both ways. The way that was just suggested by Alex, and then the way that I was originally going to do it. Oh, there we go. All right. I will assume it's close enough to balance. I'm not going to worry about the subtleties on this particular one. I've got the rubber band, marking that part off there. So let's see, the whole slinky is okay, 5.5 centimeters for the whole slinky. Just this part is, looks like 2.6 centimeters. So we have whole slinky. No, don't mess up there. Stay. So 5.5 centimeters height of whole slinky. And then height of dangling part? Dangle. What did I say? 2.6? All right, so that's the fraction there of what I'm going to be hanging off. And the mass of the whole slinky is going to stick, yep. Somewhere between 200 and 300 grams. Since we're doing a crude approximation here. So 227 grams is the mass of the whole thing. And so I'm going to assume that's mass of whole first mass of dangly part. And this was 227 grams. And so 107 grams or 0.107 kilograms. My gut tells me is that this is not an effective way or an accurate way of knowing what the internal mass is, but I could be wrong on that. So let's get this set up again. So I need to find the spring constant, and you just went through a lab where you did that, so pretty much the same process here. I'm not going to go through the full thing here, but hopefully close enough. So I'm looking at this part right here, and that's at, it's like 19.4 centimeters with just the slinky itself. Whatever I did with it. Oh, there we go. So it's 19.4 centimeters. And now I'm going to add a mass to it. Now, obviously, if I add too big of a mass, it's going to be touching the table here, which will mess things up. Yeah, that's going to be way too big.
Why not the point, the 10 grams?
All right, I'm about to change that 19. The more mass that I can add to this, the, barely. The more mass I can add, the more accurate I believe it is, that because any small eccentricities get sort of washed out with the larger numbers.
Understand.
That's my thinking, but I don't know. All right, so that. $31.9. Centimeters. All right, so now I'm going to add a 20. Now, in the lab that you're going to do on Wednesday, you're going to measure the high spot, the highest spot of the last coil, and then the lowest spot, and then take the average value. But we're just doing quick and dirty at the moment. That's about, it's like about 19.9. And that was with a 20-gram mass attached to it. So we can find Hooke's law by, well, how far it stretches. I know that, ignoring sign, that Kx, or K delta x, is equal to mg. Because we have the weight acting down on the mass and then the spring force acting up on the mass. And so K is mg over delta x, which is 0.02 kilograms times 9.8 meters per second squared over how far it stretched, which is 0.12 meters, unless I made a careless error. So 10, 1, 2, yeah, that's seeming about right. .6 something?
1.163.
6.3. Units?
You double meter.
Yes. So we have a value of K now. What we're going to do is we're going to get the thing oscillate back and forth without the 20-gram mass on it. Because the spring constant should be constant for this configuration here. If I added more coils, I'd have a different spring constant. But we're going to find the period experimentally and then calculate the mass that way of the spring. And we'll see how close it comes to that estimate. All right. Now, amplitude should not matter for the period. It's not in the formula anywhere. So I need people with stopwatches.
Okay, hold on a second.
All right, similar to before, I'm going to do 3, 2, 1, go. We'll time 10 oscillations.
One sec while I get my clock.
All right,
Okay, stopwatch.
everyone ready? All right, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 oscillations. What do we got?
10.18.
10.11.
10.11?
10.09.
I must have been slow because I got 10.32.
Yeah, I think I was slow too.
10.10?
Yeah, I think I was a bit slow. But-
Now, if we have an outlier, you cannot officially just go, I don't like that number, so let's just get rid of it. Sort of. I can't just get rid of that one. But if I want to, it is legitimate to. If I want to get rid of that one, I have to get rid of since it's the largest, I also have to get rid of the smallest. So we either keep it all in there, or start tossing out large and small. If we did it twice, in essence, we'd go for the median answer. But keep it in, throw it out, throw them out. Keep them in. All right, so what's the average here?
on 16.
10.16 seconds. And that's for 10 oscillations. The period is just for 1. So this is 1.016 seconds. We have a value for k here, so I'm making the claim that 1.016 seconds equals 2 pi times the square root of my mass of my slinky, so I'm just writing m sub s, or actually I'm going to write it m sub EFF for effective mass, over our spring constant of 1.6 newtons per meter. And what is the effective mass?
Do we divide, I forget how we do this, do we just divide both sides by 2 pi first? or-
Yes. If you're solving for something, you need to start peeling away the layers of the onion. And so since 2 pi is on the outside, get rid of that first, then square, and then multiply times 1.6.
1.075.
4.075. Anyone else get the same thing? No, I'm not buying that.
That's 1.6 for K, right?
Right?
4.07, that's what I got too. Alright, square both sides, get rid of that square root and then multiply by 1.6.
What you do with the 2 pi?
Divided the time part.
You divided 1.1.
1.016 divided by 2 pi.
Okay, and you got,
I got 1.59.
yeah, all right. What I think you did there is you did 1.016 divided, does it do a slash or the division symbol?
The division symbol on my calculator is slash.
Okay, slash 2 pi, that's what you did on your
Yeah.
calculator?
Oh, so it did 1.016 divided by 2 first, and then pi, right?
And then it multiplied by pi.
Oh.
So you need either parentheses here or do another slash in there.
Gotcha. Huh.
Classic mistake.
I got 0.042.
Like 0.042?
That's all I got.
Okay. Units?
Gram.
Kilograms. And when we did it before, we had 0.107 kilograms. They didn't. I would have expected them to be a lot closer if this technique were more valid. And I think the difference is that not every coil in this is vibrating the exact same amount. Because this is vibrating far more than this coil right here is. And so it's not an even distribution of the whole thing moving. All right, so we have an effective mass of the slinky. So now when I add my 20 gram mass to it, I now have a mass of, well, the effective mass of the slinky, 0.042, plus the effective mass, or plus that mass, which we assume is 0.02. So 0.062 is my total effective mass of this system here. What I'm taking into account with the slinky, plus what I've added to it. So, it seems too good to hope for me that we'll get excellent results like we did last Wednesday. But what the heck, let's try it. If we come as close as we did last time, you might see me do a happy dance. I don't know if that's a curse or a blessing. All right. You know, before we actually predict it, let's actually get the experimental value. All right, so we'll pull this down. Again, the amplitude should not matter, so it doesn't really matter how far I pull it. At least
Stopwatch again?
Yep, stopwatch again. I want to make sure it goes up and down. All right, here we go. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I got, okay, 12.19.
12.19,
Yeah.
I got 11.67.
0.67,
77.
77.
11.65.
Is that just the button on my side?
11.63.
63,
73.
70, 73.
Sorry.
All right. So we end up with an average.
.84.
Okay, confirmation? All right. Let's see if this works. Pull this down so that the video will get our awesomeness. Our prediction is 2 pi times the square root of the total effective mass, which is what we hung on it, plus the effective mass of the slinky, 0.062, divided by our spring constant of 1.6.
.24.
1.24.
Second.
So that's our prediction of 1.24, and what we found experimentally, again, don't forget that this is for 10 oscillations, will be 1.184 seconds. Not as spectacular as before. The places where, when you do the lab, it will be better is that when you found, in this case right here, when we found the spring constant of 1.6 newtons per meter, we had a sampling of one data point. And so it doesn't take into account a lot of other things that will get washed out if you do several data points like you did in the lab that was just handed in. So that's probably the biggest issue. Also, my measurements, probably not as big an effect, but the 0.12 meters that, I didn't take a lot of time and care, like I was doing a really formal, doing it more efficiently. And an even lesser effect, we didn't actually find that mass right there, and that is just rounded off to two significant figures. Now, I chose the bunged up slinky because, again, as I mentioned before, I wanted to pick something I didn't really have to worry about too much if it got messed up more. When you do this on Thursday, Wednesday, one of those days, I would not recommend using this, but using a bar where it's not as thick, or 2 bars so that it's more stable. Every group has figured it out at some point.
Is it just gonna be one group, or will it be, or are we gonna?
Let's find out on Wednesday. I don't know.
Oh, okay.
I've gone back and forth on that one. Any questions? All right, so let's talk about chapter 21. All right, so now we're going to get into mechanical waves. Again, chapter, 21 is right. Now, they say mechanical waves as opposed to just generic waves because mechanical waves are waves that require a medium. It does require either a gas, a solid, or liquid, plasma, something like that, in order to be able to be transmitted. Mechanical waves do not go through space. Those require electromagnetic waves
So sound is
and
an
gravitational waves.
example.
Pardon?
So sound is an example of a mechanical wave.
Absolutely. Because as everyone knows, in space,
No one can be used.
absolutely. Now, there are two basic types of mechanical waves that we're working with here. We have longitudinal and transverse. Some textbooks, although I think it's been a while, I hope your textbook doesn't do it, and I missed it. Some textbooks will throw in another one, a surface wave, and I'll talk about why we will basically ignore surface waves. And then, as I mentioned before, non-mechanical waves got electromagnetic, which is basically light, which we'll get to later. So a longitudinal wave particles, and I put particle, whatever the vibrating medium is, particles travel parallel or anti-parallel to the wave. Now, Claire's still going to do the same. Transverse waves, the particles or whatever is vibrating, travel perpendicular to the wave. As with a lot of things in physics, you generally break it down into parallel and perpendicular. In the ideal surface wave, basically a particle travels in a circle. And so the reason why, so if we had an ocean wave right here, and you looked at a bit of water here, the water basically the water basically travels in a circle. It goes forward a little bit, and then it gets pulled back. So it's parallel and perpendicular motion, and so surface waves generally are just a combination of these two, and so that's why surface waves generally are ignored in textbooks.
Would a surface wave be, would an example of a surface wave be the turbulence in a pipe, like a fluid flowing through a pipe? Or not really?
If there's turbulence, you definitely get that circular motion there. Yeah, there are a lot of other factors involved with that.
Oh, then if it's not, it's okay.
Yeah, I just hadn't thought about that too much. I think you could legitimately make the case for turbulence as a surface component to it.
But there's a lot more
But,
to it.
yeah, I think there are other better ways of describing it. So, flat surface. Okay, the other two are the main ones that we're going to be dealing with. So here's an example of a longitudinal wave. I have a slinky. Let's see if the camera can actually pick it up. I'm going to release some coils at the top, and so think about what you see when I release coils. What did you see?
Transfer down to the bottom.
And then,
It bounced up.
yeah. So that's what I saw too. So did everyone see that?
Not, yeah.
Okay. I'm going to release coils at the top.
Oh, I saw,
That's-
yeah, I saw it now.
All right. Now the particles in this case are just the coils, and the coils just basically move like this. But sometimes the coils are closer together, sometimes they're farther apart. But that's an example of a longitudinal wave. So I'm going to put down as sort of an example here, slinky pulse. Another example of a longitudinal wave is sound. Because my vocal cords are vibrating back and forth, and basically it hits air molecules, which hit other air molecules, which hit other air molecules, and so forth, till it hits your eardrum. Now I do want to throw in, I know there's really no such thing as an air molecule. When I say air molecule, I mean molecules in the air, which is a combination of oxygen, argon, nitrogen, et cetera, et cetera. But I will still, at this point, now refer to it as air molecules, and you just have to know what I mean. But sound is a classic example of longitudinal waves because, well, we'll talk about that other aspect I was just going to mention when we talk about transverse. And then in geology, you have the P waves. Pardon?
Now you're about to explain.
Yeah, P stands for one of two things, primary or pressure. I've never quite gotten clarification over if they're almost interchangeable, yet if it's generational or what, but I've been told it's primary or pressure, and so I will continue to repeat that. Transverse waves. All right, so you're going to demonstrate a transverse wave right now. You need to sort of move your chair back so you can stand up in just a moment. Don't stand up quite yet. Just get ready to. We're going to start with you, and you're going to go up and down, and when you see them go up and down, you're going to do it, and then when you see them go up and down, you guys are going to do it. This is a fan wave. Oh, you're going to spread it out that way? I'm good with that too. All right. So
like this?
yeah, and if you want to throw your hands in the air, I'm fine with that too. This is just like you're in the stadium.
As soon as he starts, or like wait till he finishes?
Now, as soon as when you see him,
Okay.
don't anticipate when he's going to go. As soon as the person in front of you see the person in front of you go, you go. All right. Oh, sorry.
Yeah. So that was the time between.
That's right. The invisible people.
Right.
That's a transverse wave. The wave went this way, but the particles, you, went up and down. So that's an example of a transverse wave. So I'm going to call that the stadium wave, for lack of a better term, unless you know what a better term is.
I heard they call, I think Mexican wave it makes sense too, because isn't that where they started?
I have no idea.
What?
Mexican wave?
Yeah, I think because it was common in Mexico for them to do that.
Okay.
I don't remember.
Fun fact, Rocket League has the record for the longest Mexican wave in a sporting event.
So you've heard the term Mexican wave also? Okay. Also, if you've been to the gym, the battle ropes,
Oh, yeah, yeah. Those are transfers?
those are transverse. Because,
You're putting it.
yeah, you're applying a transverse force to it, and the particles in the rope are just moving just up and down, but you see the wave propagate. So down battle ropes. And then in geology, the S wave, where S stands for secondary or shear. It's convenient. Or it adds to the confusion, one or the other.
When you see geology, is this like related to earthquakes, I imagine?
Absolutely.
Okay.
So this is how we have an idea of what's in the Earth's core. Because if you think about it, in a transverse wave, so as I pull up on a particle like that, I'm putting in a transverse wave, as I pull up, the next coil is responding to how much tension is being pulled on it by the previous coil. And so in order for a transverse wave to exist, you have to have some sort of bonding connection between particles. So on a table, as I pull up, because it is solid, the next part responds almost immediately. And I don't know how fast you have to do it to show the time lag between my lifting up and that side actually moving, but In theory, I pull up on this side, the other side, even though to me it looks like it moves instantly, there is some sort of lag.
Isn't that based on the speed of sound through the object? The speed of sound is how fast
It's based upon not this, because the speed of sound depends on when one particle moves, how much the other one's, it's basically it's the pushing, and the transverse wave's dependent upon the pull.
Okay.
So more of a tension than a compression. I suspect that they are very much related, but I don't know what the exact relationship is. Now, if we go back to earthquakes, since transverse waves require a pull, transverse waves do not move particularly well in air. So, for example, I'm about to potentially induce a transverse wave. How many of you have felt that breeze, other than Alex, who's apparently very sensitive?
I didn't.
Yeah. So, because as I move the air molecule, that's not really pulling the next one with it.
Well, they're not connected.
That's why fans work differently blowing than they sucking.
Wait, so say that again?
A fan blowing is not the opposite of a fan sucking. It's
Ah.
different. The air flows differently in each side.
Also, the push.
Yeah. Coming off of the
Okay.
blowing side, it's no means.
I'll buy that. So, if I have the Earth, and I got my seismograph over here. By the way, my geology knowledge comes from my wife, who was a geophysicist in college. And so she did, for part of a master's thesis, until she decided to do something different, we went up in the Bad Creek area while they were still building the Bad Creek Reservoir near the corner of South Carolina and North Carolina, over west. Let's assume that's west is roughly that way. And the way that she would do seismographs is you would take a drum with paper on it and you basically smudge it. They had this it's kind of like a candle, except it was a lot more soot to it. And she would basically rotate this drum over it, making the entire thing black, and then it would be attached to a motor, so it would rotate, and then you have a needle basically dragging through the soot.
Oh,
And
yeah.
so that when the earthquake happened and the needle shook, that the marks would show up on the paper, and then you very carefully take them back and you laminate them or spray something on them so that it's now set. So that's why I draw it that way. Seismographs, I assume, are far more sophisticated. I assume
I've
there's
seen
been some
them
progress
with,
in the past 25 years.
I've seen them more with paper. Like they use paper, they'll have a pen attached to an
Oh.
arm. But I'm pretty sure they, like in the old electroencephalographs and stuff like that.
Yeah, and I've seen those as well. I'm assuming at this point it's almost all digital, but.
Yeah, I'm
right.
pretty sure they use electronic.
So there's an earthquake that happens down here. And so when the earthquake happens, you got the two plates that are next to each other and suddenly there's a slip. And you actually are getting transverse and longitudinal waves produced at the same time. You can make predictions for transverse waves in the makeup of at least part of the Earth that we see, how long it takes for a wave to reach the other side if it's transverse, and how long it takes if it's longitudinal. Well, transverse waves do not match that prediction. Longitudinal waves do a lot closer, but through a whole bunch of sophisticated math, you eventually come to this idea that the center of the Earth cannot be solid. There has to be something that is either liquid, gas, or plasma, as it turns out to be. Because the transverse waves have to go around the long way, that's why they are secondary. Shear also, because they're pulling on it, they're causing deformation perpendicular to the wave. But the primary wave makes it through And so this is how we have some idea what's in the Earth's core, plus it also works, knowing that this is molten plasma, works quite well with our knowledge of volcanoes.
Plasma?
Yeah, the Earth's core is plasma.
I thought it was a mix of salt. I thought it was solid, liquid on the outside, solid in the inside.
Oh,
Or-
at the very core?
Yeah, the very core was solid because of intense pressure and,
I didn't think that, but again, my geology knowledge is only stuff I pick up on the streets.
maybe, yeah, that's,
I didn't think there was enough pressure to do that.
maybe I could be wrong.
But the transverse wave wouldn't get there anyway because it just has to go through the plasma phase.
Right. That's the first time I've heard that, so I'm thinking, that's new.
All right, so we are near the end of what I know about geology. We'll save the other tidbits for later. So how do I represent the waves? Now, a transverse wave can be represented physically by what's going on. If I have a string that is oscillating back and forth, I mean, this would be a side view of a transverse wave, waves traveling one way or the other. But longitudinal waves, if I were talking about sound, the longitudinal wave in reality is I've got these period places where I've got air molecules closer to each other and then farther apart. And then it builds up again.
I saw something similar to that when I was looking at a video of how a klystron works.
What works?
A klystron, it's like it's a more advanced version of a magnetron, I think it is, used to broadcast signals.
We use them as amplifiers in my radar, quite strong.
Okay.
Yeah, that's yeah,
Is that flystrom?
klystron.
Cly-
Yeah.
C-L-Y.
K-L-Y
Can't spell today.
S-T-R-O-N.
I don't ask me what spelling. I just do
You said K-L-Y.
Yeah, S-T-R-O-n. Name comes from, in ancient Greek, the name comes from waves crashing on a shore.
Ah, okay.
Which is kind of a good way of explaining that longitudinal wave. Looks like that pattern's like that mass of particles is like waves crashing on a shore.
Okay. Now, when you have particles all scrunched together like this is known as compression. When the waves or the particles are farther apart, this is known as rarefaction. Spelled rarefaction, but I've always heard that pronounced rarefaction. And the same with here, what you're seeing when the coils went all the way down to the bottom and back is you're seeing the places where the coils are closer together. You see the compression, and then the rarefaction is just behind it, sort of accentuating the compressive parts. So in the slinky, this would be, they're sort of apart, they're closer together, they get farther apart, closer together, and farther apart. Now, drawing sound this way is kind of a nuisance. You can start to see that as I went on, my particles suddenly started elongating. And so we can also express longitudinal waves similar to this, except it doesn't represent the physically what's going on like a transverse wave would, but this would be, if I was using this to describe that, this would be high pressure and low pressure, or compression, rarefaction, or high density, low density, or depends on what you're actually working with at that moment. Questions to hear? So when I draw waves in the future, I'll probably be drawing them very similar to this, and I'll assume that it applies to longitudinal and transverse. If I need to talk about one specifically, then I'll hopefully make it obvious. If I'm talking about sound, I'm talking about longitudinal waves. If I'm just talking about waves in general, I'm going to represent it this way, whichever kind it is. All right. The next bit, we're going to go out in the hallway. So let's take a small little break here and stretch legs, bring down the excitement some, and then we're going to head out to the hallway.